I cannot see the slide. Maybe. Can you see the slide
So
from the other end?
we have started the live in YouTube. I will ask the host for the slide.
All right.
Okay. Okay, can we start, Dr. Ibrahim?
Yeah, sure.
Alright. Okay, Assalamualaikum warahmatullahi wabarakatuh. And a very good morning to our speaker, Dr. Ibrahim Gambo. So it's still early in the morning there, not yet 8 in the morning. So a very good morning. And also a very good afternoon to our beloved students, lecturers of MAT 183, which is our subject. And maybe there are participants from outside UiTM Pasir Gudang too. And I would like to welcome everyone to this webinar entitled Real World Calculus, How Differentiation and Integration Shape Modern Science. I am Dr. Noida Binti Anmol, your MC for the webinar today. Alright, first of all, I would like to know our audiences first. Our students, please comment hi in your comment section. Is there anyone there? Please comment hi so that your lecturers will be aware that you are here. Hi, Adam. Alright. Hi. Okay. So that I know you hear me. Okay. So thank you everyone for joining us. So is there anyone, audiences outside, from outside UiTM Pasir Gudang? Please say hello. You can comment hello if you're outside, from outside UiTM Pasir Gudang. Okay, hi Fatin Farhana. Okay, hello Nabil. Okay, so now I know there's quite a number of participants from outside UiTM Pasir Gudang too. Okay, thank you for joining us today. Okay, this webinar is actually organized by the lecturers of MAT 183 from College of Computing, Informatics and Mathematics, UiTM Johor Branch, Pasir Gudang campus. And it is actually one of the initiatives to give an extra knowledge that is probably not in our syllabus, and also an exposure to the students to hear from the other point of view or perspectives other than from your lecturers. Okay, this session is divided into two parts, which the first session is the sharing from the speaker, and the second session is session of answer. So everyone is welcome to drop your comments on the YouTube comment section, and I will read them at the end of the session. Okay, before I pass the session to our speaker, let me introduce our speaker. Dr. Ibrahim Gambo is a dedicated academic specializing in pure mathematics with a focus on algebra and applications. He earned his PhD in mathematics from University Technology Malaysia and has over 5 years of postdoctoral teaching experience. Dr. Ibrahim Gambo has mentored both undergraduate and graduate students and has been recognized with awards such as Best Postgraduate Students Award and the International Doctorate Fellowship. So currently, he serves as a senior lecturer and the head of department, Mathematical Sciences Department at Bauchi State University, Gadao, Nigeria. His research contributions include numerous publications in reputable journals and also conferences with topics covering group theory and its applications. Dr. Ibrahim Gambo teach subjects such as group theory, abstract algebra, linear algebra, calculus, and many more. He is also serves on the editorial team of the Gadao Journal of Pure and Allied Sciences. His commitment to mathematics and education is further reflected in his active participation in academic and also professional bodies. Okay, without further ado, let us welcome Dr. Ibrahim Gambo to share your inputs. So please welcome.
Thank you very much, Dr. Nur Hidayo Alimon. And it's also nice to be invited by University Technology Vara to at least share with the students. Of course, as you earlier said, uh, on new perspective. I mean, other than the usual, I mean, lectures they usually have from their from their day-to-day, I mean, lecturers, uh, and all the viewers. I mean, those that are viewing us from the YouTube. You're all welcome. And as Ella mentioned, uh, of course, I studied in Malaysia too. So of course, I still can understand the little thing about the language, not because I don't usually speak it from this end. So the topic that maybe that is being given to me is to share on how the uh, differentiation and integration shape the modern science. Uh, of course, I hope the slide is being viewed by yes. All right. So, uh, when we talk about the differentiation and integration, of course, these are the major component of calculus, being one of the fundamental branch of mathematics. It has made a very important and revolutionized, contribution to the development of science and technology in general. Being I mean, knowing that the students usually come from the engineering background, so maybe I would like to focus my sharing mainly to the engineering aspect. That the calculus play a very big role, and of course, as rightly mentioned by Dr. Nur Idayo Alimon, uh, I would like to share actually more on the non-mathematical jargons today, because you're used to, having those dy dx in the class, and then the definite integral of a to b of all this stuff. But maybe today I would like to share a little bit different from those things that maybe you get from the class, so that you can have, a glimpse of another perspective of how those calculus, differentiation, and integration play a role in other aspects, specifically to the engineering concepts. So, of course, as I earlier mentioned, we do have three components of this calculus, or per se two aspects. We have the differentiation as well as the integration. This is what you have already knew from the classes that you had. Of course, the differentiation talks about the measures, the rate of change of things. Once you have the distance, you can be able to find the velocity, the acceleration, based on the number of the derivatives that you are having for that one. And this is one of the crucial scientific, or thing that play a very big role in science, and of course the technology in general. And on the other hand, the integration also talks about of course, the area under the cap, which we usually find the volume, the energy, as well as the other fundamental concept in engineering. So even if you put these two together, you can see that you can be able to have what we call the modeling. And this modeling usually is from the differential equation that you are having, where you come up with, trying to transform the real life problem into the mathematical form. And as such, once you get that mathematical form, any other manipulation that is mathematically acceptable, you can be able to play around with in order to get what you want. So most of the real life complex systems are usually modeled into the mathematical form, uh, and then you can apply the differentiation and then the integration to get the desired results. So now, when we talk about the differentiation, being the mathematics of change and optimization, I specifically choose these two, focus, because the rate of change is really what the 21st century is always talking about. So the differentiation, of course, play a very vital role in calculating the rate of change of a function. And this is what you have already learned from the class. And this is important because for you to understand the quantities of how they behave, they vary based on time, then of course the differentiation is the key thing to take into consideration. And then when you come to the optimization, you see, you always been an engineering student or an engineer per se, we can say that you always talk about how do you maximize the efficiency, how did you minimize the cost. That has been always the case of upgrading, updating of systems. So for you to be able to do this, the differentiation, because we are talking about the change at the rate at the change at which the change is usually occurring. So the differentiation play a very big role by allowing you to be able to maximize the efficiency of your system, as well as the minimizing the cost in that aspect. So now, if you look at this now, on the other hand, the integral calculus in general, as I earlier mentioned, is about measuring the area, volume, and then the accumulation. I try to choose these three components because they are the key things that play a very big, role in terms of engineering and designing and evaluating of the efficiency of the systems. So if you look at the area under the curve, you can see that in the class they always talk, okay, let's integrate from A to V of a certain function with respect to certain things. So in that case, this is to tell you that you can be able to find the area, you can be able to find the volume of certain solid, and then you can be able to accumulate, certain distances or certain quantities. So once you talk about the area under the curve, it allows you to calculate the area being bounded by the curve, and of course, with respect to the x-axis. And this is very fundamental key of understanding how the accumulation of quantities works. And then when you talk about the volume, is used to calculate the volume of three-dimensional objects, whereby you will have, be able to define them into infinitesimal pieces by summing them up. That's why you will have maybe the interval from A to B, where you fraction that interval into certain, sub-intervals, so that the more you reduce the size of the thing, the better the accuracy of of the of the the calculation you're going to have. So at least summing them up will now give you the precise or maybe approximate value that you intend to do. So the integration helps you to be able to find the volume of that one with very minimal error possible. And then when you talk of the accumulation, the integration allows us to understand the accumulation of the quantities over certain, of course, certain time, because the calculus entirely is talking about the time, and that is why it's always moving in with the innovative things being the cornerstone of of innovation in engineering. And now, when we talk of the modeling itself, we're talking about how these, systems have been formed, because for you to be able to do any other calculation of either the differentiation or the integration, you have to get the system. But how this system happen, that is the most important, because we're talking about how do you move a real life situation into the mathematical concept, and then being able to now manipulate those concepts in order to achieve what you desired to. So looking at the differential equations, they are just mathematical expressions that describe the relationship between the functions and its derivatives. And of course, we all know that the derivative is the key thing in the world of calculus. And then these dynamical systems, they are essential modeling that we use to determine or predict certain things. They help you when it comes to the chemical reactions, when it comes to the electrical circuits, when it comes to the population growth, or any other concept that you think that you want to determine that has to do with time, movement, and any other thing. Then these equations also helps us to understand how these systems behave, because the behavior of these systems will help you to, to determine the kind of change that you need in order to inculcate in the behavior of the system. And that is why, if you look at your handphones, they always, the new version of this, certain latest version varies with the previous one. All they are using to predict this kind of behavior, they are using the concept of, of differentiation, because they determine the rate at which these changes, happen, and what are the focus of the customers, what are the focus of the users, what do they focus on when everybody is moving toward the virtual thing. So they try to enhance the cameras. When everybody is moving about the improvement of the circuit or the system, they now upgrade from 2G to 3G, from 3G to 4G, now to 5G. So all these changes are happening because the calculus give the room for that one, and it really, predict and accurately determine how that thing usually happen. So now, if you look at this general application to modern engineering, you know, of course, there are three things that once we talk about engineering, the whole focus is on that three things. The first one is about the design, and then the analysis, and then the optimization. When it comes to any other system in the world, uh, these three components are the major things to take into cognizance. Now, when you talk about the design, of course, the calculus helps the engineers to design the structures when it comes to the civil engineering. It helps to design the machines, the systems, and then this design of whatever structure, machines, or system has to do with three things. These three things is about the efficiency, the safety, and the performance. Whenever you are making a design of any given system, which I know the engineers much, know much better, you have to take these three things into consideration, and that is the efficiency, the safety, and the performance. But this can only happen if the right calculus is being employed. Then when it comes to the after the design, then you have to go for the analysis, because you have to analyze the behavior of the system, and then now you predict how this system that you earlier designed can respond to the various inputs or conditions that is being given to them. Either it is the robotics, or either it is the artificial intelligence, or any other machine learning that you may think of. And then, of course, we talk about the optimization. Calculus give us the right, avenue for us to optimize the whole of this system. You already design your system, you analyze the system, but the next thing is how do you optimize the system? And this optimization is what brings about the performance, because it's only when you, optimize the system that you'll be able to know the performance of your system. And then you now try to ensure that if you are talking about the structure, how this structure, can withstand, can withstand pressure. If you're talking about the circuits, and then maybe all signals, then you can see how this system can withstand, the signal without having any break. And then, of course, all these things, as I earlier mentioned, when we talk about the optimization, you see how you can increase the performance, but at the same time reduce the cost. That's what we talk about the optimization. And in this case, that's why you will always, when you come to the normal classes of your calculus, you see that you have the maximum and the minimum. These are the things. You maximize the performance, and then you minimize the cost. Now, specifically, if you look at the concept of civil engineering, I took three things because the whole engineering, civil engineering, focuses on the fluid dynamics, structural analysis, as well as the transportation planning. So when it talks about the fluid dynamics, this is the water resource engineering that, the calculus give us the opportunity to model this kind of system to be able to determine the flow of fluids as well as the, the essential designing of bridges, as well as dams and pipes. This all has to do with the water, the flow. It has to do with the movement, and of course the sustainability of this kind of system. So generally the calculus give us this because we model these real situations into the mathematical form, and then of course we applied the concept of differentiation to be able to determine these changes, because we talk about the fluid dynamics. It really changed. So how does this change occur? Of course, this is the main idea of the differentiation. That's the rate of change, and of course it varies based on time. And then when you go to the structural analysis, you can see that the engineers can use the calculus to calculate the stresses and the strength of these structures, as I earlier mentioned. Because when you are designing the buildings and the bridges, as of course, one of the key component of any, of course, concept of engineering is about the safety and the stability. So you want to know how safe is this kind of structure that you put in place, because it has to do with the life of people, or maybe it has to do with the lifespan and any other thing that you may maybe take into consideration. And then when you talk of the transportation planning, this the same calculus is used to optimize the traffic flow, because once there are movement, once there is movement, there is calculus. That is one thing. And once there is change, there is calculus. Once things has to do with time, there is calculus. That is the whole thing. So once you come into this one, now if you talk about the transportation, you are talking about the traffic flow. How do you design the networks so that at least you will have a better route, the shortest route possible? And then how do you manage the transportation systems effectively? All this, if model from the real life situation, because you're just like putting them into mathematical form. That is just about the modeling. It's not something very big, or it's not something very alien. It's something that you have been doing in the classes, and then of course taking the real life situation will give you a better view. Now, if you look at the mechanical engineering, also in this case, I try to limit, of course, the whole thing into the three things, which is the thermodynamics, kinematics, and then the design optimization. We're talking about the mechanical engineering. So if you talk about the thermodynamics, you are talking about how did you model the heat transfer, because how did you have the energy conversion from one form to another. You can be able to see, okay, we have this kind of energy or mechanical energy to another form of energy to give you light, so you transform it into the electrical energy. So this kind of a conversion only is possible if the differentiation is being applied into, and then this will help you to determine the behavior of this kind of engines, or even the power plants, because from the power plants you talk about the mechanical energy into the the electrical energy or power energy per se. Then you now talk about the kinematics. The calculus is essential for analyzing the motion of objects, including the design of robots, vehicles, and then other machines. So this is the kind of kinematic things, because we're talking about the movement of these energies, unlike the potential energy that you're having, which is energy at rest. So you're talking about the the energy in motion. So calculus play a very big role, of course, in analyzing these kind of things to be able to improve or optimize the design. Then when we come to the design optimization, as I earlier mentioned, any system that is being designed requires optimizing. That's why you will always have an update, you will always have an upgrade of this kind of systems. But these upgrades and systems can effectively, take place if the calculus or the right calculus is being employed. And that is why you will see that to be able to get this kind of system, you have to, maximize the efficiency, the performance, and at the same time, reduce the cost if possible. So this is the whole thing that maybe you may have as an idea with regards to the mechanical engineering. Now, if you go into the chemical engineering, you can see that we are talking about the reaction kinetics, mass transfer, and then the process control. For those that are in chemical engineering, may of course understands better how this kind of things happen. Even in your introduction to the course will give you the idea of how these things have been processed. So the calculus help us to model this rate of change of these chemical reactions, and of course optimize the production process. Because if you're talking about the chemical reactions, you're talking about the production. So how did you optimize this production process, and then how did you now make the to control the movement of the materials between one different phase to another different phase of separation of processes. And then the last thing is about how this processes have been controlled. Of course, the calculus is used to design and implement the control systems to ensure this safety and efficient operation of these chemical plants. Of course, as I at the beginning of my talks, I made mention that these three things are very, very important in any design or any development that you can maybe think of as far as engineering is concerned. The safety, the efficiency, and then of course the design itself. So now when you come to the mechatronics engineering, of course the main thing is about the feedback control system. Of course, when we talk of mechatronics, we talk about the robotics and then the automation. All these automations that we are seeing, where you will have all these machines working in place of humans, or as maybe at least improve the performance of humans in at least handling some parts of the things, requires this kind of things, require the feedback control, and of course how the whole thing make the movement. So the right concept that is always maybe employed in this case is definitely the calculus. The calculus is used to design these control systems, make the adjustments of the behaviors of these robots or whatever automated systems that you design, and then of course help you to accumulate the data, the real-time data, because it's only when you get the data that you can be able to make the right enhancement or a right movement of this a right optimization of this kind of complex task. So all these feedbacks, the robotics as well as the automations, we get them from the right calculus or differentiation or integration that you employ. That is why I would keep on saying that the differentiation is talking about the rate of change with respect to the time, because we're talking about the real thing. So anything that is real world, definitely it has to do with the time. So this kind of changes, movement, and whatever that you are getting with respect to the time is handled based by the calculus, of course, specifically by the precision part of the calculus. Now, when you go to the electrical engineering aspects, when you go to the this one, we talk about the electromagnetics, circuit analysis, and then the power systems. When we talk of the electromagnetic thing, we are talking about how did you model the behavior of these electric and magnetic fields. This is very essential for designing the antennas, motors, and then the power systems. So, of course, in this concept as well, the calculus is always been in place, because once you want to make a design of antennas, definitely you have to see, okay, how does this going to behave? This kind of behavior can only be modeled using the differentiation or using the calculus in general. And then how does this motors, as I said, you are talking about, transferring one form of energy to another form. So, of course, the designing of these motors as well as the power systems all there for us to, to explore using the concept of calculus. And then, of course, the circuit analysis. You don't only design, but as always, you have to make an analysis. How does this analysis take place is based on the time, because as the things is going from one form to another, then so also the what the improvement or the analysis of that kind of movement that maybe you are talking of. So this kind of behavior of these electrical circuits are usually been done using the calculus in order to have an efficient operation. And then, of course, when we talk about the power system, it's not about the generating of the power, but how do you manage this power? How did you manage these grids? There are so much, danger, so much, risks. So how did you ensure the reliability and efficient of this power distribution? So all these ones, there are specific, a particular, concept that, of course, those, concept that you are learning from the classes of, okay, you will have the first derivative, you will have the second derivative. They are the same concept, the same way that you're going to apply in these kind of things. It just depend on the scenario or the real world situation that you take into consideration. That's why you will see that when you come to the differentiation, you will have different form of that one. Okay, the summation of these things, you will have this kind of product rule, chain rule. These kind of product rule, chain rule, and the quotient rule are the one that are giving you the room to make this kind of innovation, to come up with the new things. Because for you to come up with new thing, you have to add of one thing or the other. In that case, that is where the issue of this kind of rules, they come in, depending on the behavior of the things that you want to put together. And then I want to go to the electronics engineering. We talks about the semiconductors, the signal processing, as well as the communication. Of course, in this 21st century, communication is one of the advancement thing that is taken seriously. Of course, currently I'm in Nigeria, but at least most of the audience are in Malaysia, which if I'm to take a flight, it's like almost more than 19 hours flight. But I'm sitting in my own room, and at least everybody is at his own room, but listening to all these kind of things. But the right concept that gives us this kind of avenue or this kind of this kind of technology to thrive is the concept of what? Of the calculus. That is why we said it's all about, once there is time, then there is calculus. You don't need to think two way about it. It's only for you to know which type of concept from the calculus that you have learned so far can be employed into that kind of of your scenario or situation that you are talking about. So this calculus, of course, in the electronics also model the behavior of these transistors, the semiconductors devices, and then this kind of devices, they are the modern gadgets that are being put in our buildings to get this kind of automation things. Once there is this movement, then maybe the light will just come up. All these automated things, and then once there is no any movement, then everything will just turn up to save energy and all this. So this kind of behavior can only be modeled using the concept of calculus. Likewise, when we talk about the signal processing, it's used to analyze the process of these signals, enabling us to communicate. Of course, most of the communication are wireless now, and then if you are to use even the wired ones, you can be able to record, play, and generate images, even using the AIs, and then as well as the machine learning in general. And then, of course, I already talks about how does the communication take place. You have this kind of the satellite communications, the cellular networks, as well as the internet, the modern communication things that we are having. But all these ones actually happen because of the concept of the calculus. And then now Of course, we know we talk about these things in maybe different aspects of the engineering. Now, this particular concept of calculus give us so much, advantages, especially in this 21st century. The, the calculus, of course, is the cornerstone of any technological advancement. There is no advancement of technology or science or modern science that you're going to talk about that calculus will not come in. That is one of the takeaways that we have to know. So, in general, calculus remain an indispensable, tool that is essential, in understanding or shaping our world, because we need new advancement. We have new ideas. How do you actualize those ideas? You only need the concept of calculus to put them into reality. And then, of course, the current, the most current trending of technological advancement or science in general, or modern science per se, is the machine learning. And this concept of machine, the whole concept of machine learning is behind the, of course, the concept of calculus, and it is one of the core mathematical concepts. And this enables us to understand the inner working, different of machine learning algorithms, because you want to design an AI, or you want to design a kind of robotic machine or whatever. The inner part, the behind the scene concept that always been employed, either knowingly or unknowingly, is the calculus. So for you to have any innovative, uh, modern, and of course dynamic thing, you have to employ calculus. You want to have a modern, prosperous, and very efficient thing, calculus is just there for you to help you. And then, of course, the application of this calculus continue to to expand every single day, and as complex systems continue to strive, so also the challenges of this century that we are in, as it continues, so also the coverage of this calculus and its application also expands. So calculus also go with the modern, modern innovation, and also modern advancements as we're having in the real life, because they are, as I mentioned, is the cornerstone that always give us the room to be able to design those kind of systems, and then be able to have the systems in a much better, friendly, efficient, and also valuable way. And then, as the kind of conclusion, you know, the recap that maybe I can say on this one, because as I told you, I just want to avoid the mathematical jargons in this talk, uh, because that has been the things that you have been learning from the class. But how did you apply this kind of concepts that you have learned from the class into the real life situation? Or what do you think are the prospects? What do you think are the are the advantages of these things that you have learned? What are the the what are the importance of all these things that you are learning from the class to another form of uh, you know uh, of real life situation? So in order to do this, there are so many impacts of this calculus in this modern science and technology, and it has of course played a very vital and pivotal role in sharpening the modern world, and of course powering technological advancements and then driving the scientific discoveries. Of course, if you talk about the I mean the application of this calculus, of course it cannot be major. So it just depends on the situation that you find yourself. It's just on the situation that you get maybe into consideration. It just depends on the scenario or on the concept that you're having at hand, or it depends on the complex problem that you're having, so that you can be able to make that kind of model. And this model that I already mentioned, it's not something big, but just transforming the real life situation into mathematical form. That's it. Transform it into the mathematical form. Now use your mathematical manipulation that are, of course, acceptable, usually the calculus, and then you transform it back to the real life. Then you'll see something very amazing. And that's why each and every year you will see that there is one form of advancement or the other. This is because the calculus is in play and it always continue to evolve, and it will always remain the indispensable tool for solving complex problems and pushing the boundaries of the human knowledge in general. So once you're talking about the human development, not only the modern science, you talks about calculus, and this is the one of the most important and valuable uh, you know fundamental importance of this calculus in general. So I think with this, because I was thinking of, okay, where do I focus? If I take I have so many mathematical things to say. Okay, I have this real life, I can be able to do this, but I am like, okay, I shouldn't be biased, so that I will not take one aspect only and then leave the other aspects. But the main key point is that every aspect of the engineering can be modeled and transformed into a mathematical form that can be manipulated using calculus. Tarimekase, thank you very much. This, I think, will be the end of the sharing, and I look forward to have some questions, maybe specifically on certain things, so that that can be responded. Thank you very much, and back to the MC and the moderator.
Yeah, thank you very much, Dr. Ibrahim, for a very informative sharing. So I think you have covered almost all engineering parts, the applications of engineering that we have not learned in our class. So now I will open for the question and answer session. So I will read the questions. Okay, so there is one question. I'm curious. Okay, that one. I'm curious about the role of calculus in the development of technology. How do software engineers use calculus in practical application like machine learning or data analysis?
All right, thank you very much, Mohammed Arif. Yes, I'm happy that you're curious, because in mathematics, we always want to make you curious, because it's only when you are curious that you will be able to come up with something that is very meaningful, and innovative. So when you talk about the machine learning in general, you are talking about, the behavior of learning a certain real life situation to predict, the next thing that will happen. And for you to be able to have this, you have to get, of course, you have to get the data. Uh, the timeline that you wanted to use in order to make the prediction, and that is why the higher the prediction, the higher the data, the better the prediction. So when we talk of the machine learning specifically, the concept of differentiation specifically is the one that is helping in making the data, cleansing the data that you have already garnered. Then this data will be used to, using the concept of differentiation to determine, okay, what are the kind of possible data that will happen in the next certain time. If you have gathered your data for, let's say, one hour, so what will happen in the next 2, 3, 4, 5 hours is the concept of the differentiation that will tell you that, okay, this is the way that you can be able to, or maybe this is the behavior of your data, and this is the way that you are going to have the next prediction. And then, of course, the data analysis just depend on the time. What kind of analysis do you want to analyze? That is the key point. If, let's say, you wanted to have a kind of one data from one form to another and then merge it into another concept, then that is where the sum of differentiation comes in, because you model one data into the one mathematical form, and then you model the data into another thing. Let's take, for instance, you wanted to determine the acceleration of a certain distance or by a time. You have the equation of that distance with respect to the time that you're having, and then you have another set of equation of distance with respect to the time, and then you wanted to see, okay, how does this behavior of this maybe distance compare to the other one. It depends on what you want to do. That is why the issue of the sum of differentiation or the chain rule comes in, because we're talking about function in a function. So usually in the machine learning in general, it used the concept of chain rule. Generally, the major concept of calculus that is applied in machine learning is the chain rule, because it's a function inside a function inside a function, and that is how that machine learn from that behavior and come up with the desired or specific thing that you are in need of. So it depends on the problem that you are having at hand, or the complex nature of the thing that you want to take into consideration. Thank you. I hope this gives you the concept of maybe of the thing that you may likely like to know from that one.
So thank you very much, Dr. Ibrahim. It's very interesting. Is there any questions from the audience? Any other question? You can drop your comments. The rest of students, we don't have questions. Okay, Danish. May I know how the engineers use both differentiation and integration to analyze the interaction between moving fluids and mechanical structures, such as underwater pipelines?
Yes, thank you very much, Danish. When you talk about the general, you talk about the fluids and the mechanical structure. This is, has to do with the water resource engineering. In the underwater pipelines, we always try to model, it depends on the movement of the fluid, and it depends on the fluid that you're talking about. If it's the normal water, you're talking about the movement of that water. If you're talking about the gas, you're talking about the petrol or any other, it depends on the fluids in general. So these kind of fluids, they are now being modeled based on the distance they need to travel. And then if you are to maybe see, okay, because you just want to see how the interaction of, the interaction between the fluids and the mechanical structure. Of course, it depends on the nature of the fluid. If the fluid is heavy, the mechanical structure of moving that one is going to be, is going to be very, very slow. But if the fluid is lighter, then the movement is going to be faster. But in this case, the concept of differentiation that you are going to apply in there is usually you apply the concept of of the quotient rule. Why do you need the quotient rule there? Because the movement of the fluid is proportionate to the mechanical structure in terms of the size of the pipe, in terms of the the distance that is going to cover. So in order to have that kind of a relationship, you definitely need the concept of quotient rule, because that is what determines the ratio at which the fluid is going to make the right movement. So we apply the concept of quotient rule mostly in modeling the fluid and movement in the mechanical structures, and likewise when it comes to the integration, usually I know you learn about the volume of finding the volume of a certain structure, and that is the way you find the volume depending on the structure of the thing that you are looking for.
Okay, thank you, Dr. Ibrahim. Okay, so we move to the next question.
Right.
Could you please give an example of real-world problem where integration led to a significant innovation?
Oh, this is everything that has to do with time. earlier, everything that has to do with time, because, oh, you're talking about, yes, because you know, we talk about once there is an interval, that's why you learn about the definite integral, you know, between A to V, that you wanted to find either the volume or the area of that particular thing. So once there is a starting point and then there is an end point of anything that you want to find, integration will definitely you know, play a role, and not only play a role but will lead to a significant innovation. Anything. If you can give me one example, I can just give you a kind of, you know, a way that you can be able to model that. That's why I said even the set intervals, they are being divided into the sub intervals, where you will have this, you know, sub intervals to be able to define the things into small other intervals to be able to make your own innovation. So it just depends on the things that you want to make an improvement on. But especially in the AI, because you are talking about the significant innovation, I think one of the most important innovation that we're having now is the AI. If you look at the AI itself, it will only always tell you that it's always learning. Why does it learning? Because it's now accumulating the data, the inputs that you are giving it. So that kind of accumulation is the concept of integration. Yes. So you always accumulate those data. The AI machines always accumulate those data and is always learning from that data that is being inputted to it. And then, of course, the fact that it gets data from different sources, so it makes the comparison between those data and see which data appeared frequent more. I mean, in terms of number, and then it can be able to now go biased. That's why the AI may not be true all the time, because it is been learning only based on the information that is being given to it. So the major and the important, concept that is in AI and given this kind of significant, I mean, innovation, is the integration, because it's the accumulation of those information that is being inputted into the into the AI. Thank you.
Okay, thank you, Dr. Ibrahim. Is there any question from the audience? Okay. Okay, maybe last from me. Okay.
Yes.
Okay, I just want you to advise the students because they always ask me about the applications of engineering. So we learn about the fundamental part in the calculus in our syllabus, but what are the applications of engineering? So today you have already explained to them for the applications in each engineering part. But what can you advise them and on how the importance of to master, to understand the fundamental parts?
Thank you very much. I think this should be the takeaway, and I'm happy that you have given the last, you have given it as a question, as the last question in this aspect. You know, generally, what you have learned in the class shouldn't end in your book. That's one thing that you have to understand. Let it be a kind of tool that will help you to understand other things better. You are taking physics just the way you are taking mathematics. Try to relate this thing. Now, you are taking engineering design just the way you are taking calculus. Now, try to establish, because that is always how you go about it, establish a relationship between this calculus with this engineering design. Because in the engineering design, let's take for instance, if I come to the, if I come to the physics, I have, maybe I can be able to say, okay, I have this equation of distance over time. Then I wanted to find the acceleration, I wanted to find the velocity. If you are talking about the physics aspect of it, you can be able to just of course apply the formula and get this result. But this calculus also give you that, okay, once you make the derivative of this one, you can be able to get this one. And once you derive it, I mean, you differentiate, I mean, that particular concept, you also get another concept that you are in need of. So it's only when you are making a kind of mapping between what you have learned from that class to what you are learning from the other concept of the specifically for the engineering design and everything, then you can be able to see the application there. Of course, even those softwares that you have been using, they apply that concept. If you are to go to the behind the scene, concepts of those things, you will clearly see that rate of change with time is just something that has to do with the calculus. So for me, it's always about making a kind of a mapping between what you have learned in of course what you have learned in the mathematics. Sometimes you will feel like these are just jargons, that maybe let me just try to pass this course and forget about this. But it's not all about that one actually. It's about how you translate that what you have learned into the other concept or other areas that you wanted to work on, and that should be always a kind of a guiding principle for you. I have learned about the I mean the chain rule. So how does this chain rule behave? The chain rule being divided into certain, depending on the number of functions involved. Maybe you have this one. So it means this is giving you an example of, of how the expansion will go depending on the things that you understand.
Okay.
Uh,
Maybe this is the last question. Okay, how deeply do I need to understand calculus as an engineer? Should I understand every proof? Should I just know how to apply calculus without understanding why it works?
this is a very, very, very interesting question from Arif. You know, uh, you have to understand calculus as much as you can. That is one thing. Because the better you understand it, the more application opportunities that it will give you. So learn it as much as you can. That is how deep you can learn it. You don't need to stop at any given time, like, okay, I just have to understand the proof. No, why should you understand the proof? Because those proofs are just telling you how do you arrive at those things. Because in mathematics, we don't always say, okay, 1 plus 1 is equal to 2. How does it become 2? That is the most important thing. So how does it becomes two is something that will help you to, to know the behind the scene, the process at how you arrive to that one. So for me, as an engineer, just learn it as much as you can. And then of course the proofs are not so much important, but how they work actually. How they work. Yeah, should find the middle ground. You already have the middle ground because you are an engineer already. That is your middle ground because you have the major that you wanted to specialize on, and you have the fundamental concept that is broadening your your perception, your thinking, and easing your work. So you already have the middle ground of that one. That's very interesting question, actually.
Okay, thank you very much, Dr. Ibrahim. So I hope all the questions have been answered. Okay, so I think that's the end of the question and answer session. Okay, thank you very much, Dr. Ibrahim Gambo, for your very informative sharing and very interesting. I hope all the students and all the audiences, either you are from UITM or outside UITM, so I hope this sharing session will benefits all of you in engineering parts, in real world applications, and understand better how differentiation and integration shape the modern science. Okay. So before we end the session, so I would like to remind all the audiences to fill in the feedback form. The host will put the link in the comments. So, all right. So you can click the link and make sure you fill in the correct full name and also the correct email address because you will get your e-certificate in your email. Okay, so we will close the forms in 15 minutes. Okay, so let me take some photos of us, Dr. Ibrahim.
Okay.
Okay, this is for memories.
It's
Okay,
okay.
1, 2, 3. Okay, 1, 2, 3. Okay, so all of them say thank you, Dr. Ibrahim, for the answers. Thank you. Prof. Niza is also here. Thank you, Dr.
Oh,
Ibrahim.
that's very good. We have to acknowledge that. Thank you very much, Prof. She's our mentor actually.
Yes.
We really have to acknowledge this because most of the most of the shares that we have come up with, of course, are the things that we have learned from her. So, of course, I would like to use this opportunity to thank the university as well as the College of Computing, Informatics, and Mathematics for giving me this opportunity to to share a little bit with the students, and also to thank Prof. Niza for always being supportive to all this thing. Oh, Dr. Atira also is here.
Yes.
You see so many people, so many familiar faces. Thank you for your support, and I hope I were able to give some certain things that maybe will be a takeaway to the students
Okay.
specifically. Yes, and we look forward for further, sharing if the opportunity is being availed as well.
Okay. So I think that's all for the session today. So thank you very much, Dr. Ibrahim, and thank you very much, everyone, for joining us. I hope it is very beneficial to all of you, and I believe it is very beneficial. Okay. Okay, don't forget to
Thank
fill in the attendance. Okay, thank you very much, Dr. Ibrahim. So
It's my
we
pleasure, actually. Thank you very much,
hope to see you
Dr.
again.
Nur. Yes,
Terima kasih.
sama-sama.
Okay.
Yeah. Oh, Dr. Nur Munirawan Mohammed. That's
This
very
is my
good. Thank
colleagues.
you so much. Yeah, all right. Thank you so much.
Okay, you are welcome. Thank you, everyone.